Cardinal Richelieu said, "What could you do with 6 lines from the hand of the most honest statistician?" And in this question, we want to talk about multiple relationships in data and using that to make more informed predictions. Because we've talked about linear regression where we have one factor and one coefficient to make one prediction of one value. But what if the linear relationship is multiple things and a linear combination of multiple things providing our resulting value that we want to guess? In other words, what if we have 3 data sets and the thing that we want to predict is some linear combination of those 3 data sets, and there's not one coefficient that we have to guess, but 3 coefficients that we have to guess? Well, I'm glad that I didn't recode that very simple brute force search because it would take forever to search through this space. What we can think is if we were to do a simple singular linear regression here, we can say, oh, y is related to x is 0, x is 1, x is 2, and you can see the r values aren't that great. Well, the reason these r values aren't that great, despite this being a very clear linear relationship, is y isn't related to just x is 0, just x is 1, just x is 2. It's related to all 3 of them simultaneously. There's not one slope. There's not one slope. There's actually 3 slopes, but there is one intercept. Now, how do we figure out what these values are? Effectively, what we're trying to do is solve an equation like this. Instead of finding the 1 beta and the 1 alpha, we're trying to find the 1 alpha and these 3 betas. And how would we do that? Well, if we look at this and we try and remember back to our linear algebra, we might say, oh, well, if the x's value is like a column vector going down here, this one's a column vector here, this one's a column vector here, and this is a unity value. And these are the coefficients that we want, b0, b1, b2, and alpha, then that would be equal to the column vector of what the values that we see. And if we look at something like that, we say, oh yeah, I know how to solve that. I'll solve it in a really dumb way, a really inefficient way. I'll just take the inverse of this matrix here and multiply times both sides, and that should reveal each one of my coefficients, each one of my slopes, and my intercept. And in fact, that works. These are the slopes and those are the intercept for relating these 3 data sets via multiple linear regression against that one target. Now, if I'm going to approach it this way, rather than do this very inefficient inverse and this very numerically questionable inverse, I could use something like NumPy least squares, and I end up computing the exact same values. Or I could reach for stats models. And stats models does have the ability for you to say, hey, I think that y's is related to some linear combination of x's plus x's plus x's. Tell me what you think is happening. And when you ask stats models to perform that fit, it will tell you, these are what I think the parameters are. You can see these parameters tie out. In fact, stats models can even tell you how good of a fit it thinks, and it says, oh, this is a really good fit. 99% is explained by these parameters. And that should make sense because I've constructed this data. I mean, pretty obviously that there's a relationship here. And so 99% is I'm pretty confident that's a good R value. Now, if I choose to use scikit-learn, I could use scikit-learn. It would give me the exact same intercepts and coefficients. And what I want to show you is there is a hidden relationship here. And I wonder if you can spot it between multiple linear regression and something that we've seen before. When I look at that r squared value, let me show you how it's computed. That r squared value that stats models was giving me is being computed in this fashion. I have my data, I've done my linear regression, and that gives me my coefficients and my intercepts. I can use that to construct what my guesses are. I know what my actual values are. With my guesses and my actual values, I can compute what the difference is from my actual values, and I should actually make these a little bit more consistent, like that and that, much better. I can compute what the total deviation is for my actual values. I can compute the sum of squares of the deviation between my guesses and my actual values. I can compute what I might call the residual sum of squares, that is the squared sum difference between the actual values and the guess values. And it turns out my r squared is just my residual sum of squares divided by my total deviation, or 1 minus my residual sum of squares divided by my total deviation. Now, This should be sort of reminiscent to when we do this with things like MSE, but there's something else that might come into mind when you see sum of squares and computing all sorts of sum of squares. See if you can think where we've done something like this before. But I'll leave that for you to figure out, and why don't we move on? We'll talk a little bit more about multiple linear regression. Our goal with multiple linear regression is to figure out how to take not one variable, but multiple variables in some linear combination and to figure out what the coefficients are. But there's something that's gone a little bit hinky here. Instead of 5 completely distinct data sets, data set 3 is actually just a very simple linear combination of data set 0 and 1. And data set 2 is actually determining what data set 4 is. And the actual values that I'm constructing are determined from x is 0, x is 1, and x is 4. So one of the things you can see is, here, if I try and do my linear regression, and I assume that all 5 of these are related, well, it gives me the best slopes and intercepts it can give me for these, but something's amiss, because you'd think that x is 3's contribution doesn't really tell you anything that x is 1 and x is 0 don't already tell you. And you can think something weird is going with x is 4, because I assumed it was part of what was contributing to this value, and it was part of what was contributing to this value, and I assumed that x is 2 was what was contributing to this value, but x is 4 is affecting both the input data and the output data. It's confounding this in some fashion, and this might lead us to a very important question. We don't always know what the factors are. We don't always know what the parameters are for our linear regression. And there might be some issue where some of the parameters that we suspect or some of the parameters we're putting onto our model might already have linear relations within them. And this is going to give us beginning to give us a little bit of dodgy data. Or it may be the case that one of the parameters is affecting both the input data and the observed output data. Where does that lead us? Well, how do we pick which of these values in linear regression to actually compute coefficients for? How do we decide what these are? There's a couple of approaches that we could take. We could take a bottom-up or top-down approach. We could say, you know what I'm going to do is I'm going to assume that none of them contribute, and then I'll try each one of them in independence and see what I get as an R value. And then I'll try 2 of them, see what I get as an R value. Then I'll try 3 of them and see what I get as an R value. Then I'll try 4 of them and see what I get as an R value. And see 5 of them and see what I get as an R value. And see which R value is the best. That might be one approach that you might take. But largely, one large question hangs over us, which is, how do we determine whether or not we should include a variable in our model? And critically, what happens if one of these variables is not independent of the other, but is in fact a linear combination of the other, or if it's the case where something affects both the inputs and the outputs? And none of these mechanics here are going to fail. It's not the case that any of these will fail. These will all just work. But you may start to get coefficients, and you may start to get values that are either overfit, that are not making good predictions, that aren't actually effective in practice. One thing that you could do in this circumstance is you could take your correlation and you could look at the correlation of all of the potential inputs. And if you looked at the correlation graphically of these potential inputs, you could see where there was that strong linear relationship. It is pretty clear that x is 4 and x is 2 have a strong linear relationship with each other, and it's pretty clear that x is 3 has a relationship with x is 0 and x is 1. And that might help me in my model construction to say, you know what, I'm just going to look at x is 0, 1, and 2. 3 and 4 may not be giving me information that 0 to 2 do give me. And you could compute the linear regression without them, compute them with, and you could see some of that in the R values. I should take a step back, because the thing about the R values is the more variables you include, the R value only goes up. But that's not really the case that you're making a better prediction. And so that R value and that top-down and bottom-up approach can sometimes be misleading, because the R values can say, oh yeah, doing a great job, keep going. The more variables you add, the better a job you do. When in this case, it is pretty clear x is 3 does not give you any new information. X's 4 does not give you any new information. They're exactly determined by the information that you already have in X's 0 to X's 2. And so there is a large, outstanding question about how do we make sure that the underlying terms themselves are independent, there are no confounding variables. How do we really assess what variables we put into our regression model? That's a very complex and a very difficult question for us to ask. And so I'll leave it for you to think about a little bit while we discuss why is it that we care? Well, it's pretty obvious why we care. If we have the ability to take multiple variables and use them to predict some output variable, and we're pretty confident that we've picked the right variables and they each carry unique independent information, then we can actually start making real predictions. We can say, I can't observe this particular value, but I fit against my training data, this particular linear combination, this set of linear coefficients, run it against where I think the future data is going to be and see how it pans out, but I can make predictions about where that future data would look like. I can make predictions about things that I cannot observe from data that I can observe.